is the gas mileage decreases about 8.372 miles per gallon. The intercept, so y-intercept is where x is 0. Again, this won't all, usually y-intercepts don't make a whole lot of sense because a lot of formulas are never really designed for you to plug in 0 for x. But it still does, we can go ahead and have the idea of it. So if the x was 0, so if the weight of the car was 0, then the predicted miles per gallon would be 48.741. Again, that doesn't make a whole lot of sense. You can't have a car that weighs 0 tons. So we see a strong negative linear relationship between weight and gas mileage. Let's look at the last one here. This one now is from the health data as well. We'd look at the pulse rate, beats per minute, versus the cholesterol, milligrams per deciliter. And let's try that one. So I'm going to put that into StatKey and see what that looks like. Okay, we're going to put it okay. Ooh, okay. So this is one of those no relationship at all. The dots do not seem to be following this line hardly at all. How can I tell? Besides my eyes tell me these dots are not following this line. Also, you'll kind of notice that this line is starting to look very horizontal. That's usually a good sign that you may have no linear relationship. What happens is if there was no linear relationship, the R value will start to get really close to 0. So let's look at it. Correlation coefficient right here. Yes, our R value is 0.056. It almost looks like a p-value. But an R value of 0.056, that's on the number line, that's very close to 0. So that's not telling you that there's a positive linear relationship. This is telling you that there's no linear relationship. Remember, you got to be usually in the 0.2s or 0.3s to even be considered weak linear relationship. This one is 0.05, so you're really close to 0 on the number line. Now, we learned in the last lecture that this slope, this correlation coefficient, is actually connected to the slope. So as this number goes to 0, the slope also goes to 0. So this number's slope is 1.167, is also now getting very close to 0. So that's why this line is starting to look horizontal. If you remember in your algebra days, when a line has 0 slope, it starts to look very horizontal, right? It's a horizontal line. So the more horizontal you see this line look, usually is a sign that this data is really not fitting this regression line. I do not want to use this regression line to make predictions. We can see the slope and the y-intercept. Again, I don't put much stock in these numbers because, again, we don't have any correlation, any linear relationship. This would have to give us some linear relationship in the correlation coefficient for these numbers to really take on an accurate meaning. But it's good to practice, though. Remember, slope would be increase or decrease in y per unit of x. So this would tell us that the cholesterol is increasing 1.167 for every 1 beat per minute higher the pulse rate. The y-intercept was if the x is 0, what's the predicted y value? So if pulse rates were 0, which again, that's not going to happen, the cholesterol would be 233.042. Okay, so again, those numbers don't actually are not accurate because this doesn't have a linear relationship. Now let's go back, let's go to Statcato now, because while this is great, this is actually great for the basics, like getting the slope, the y-intercept, and the correlation coefficient. Statcato gives you all the advanced stuff. So if you're going to do some of the more advanced kinds of graphs and advanced kind of residual studies in correlation and regression, you're going to need a program like Statcato for that. So here's my same 3 data sets in Statcato. So here, let's look at our waist size and our body mass index. By the way, you can make, if you just want to make a scatter plot, you can go to the graph menu and just click Scatterplot. It'll ask you to pick the x and the y variable. So again, I'm doing waist size as my x and body mass index as my y. It does have this weird button, Add Series. So don't forget, if you have to click this Add Series button. I guess that means you're putting these 2 data sets together. And then it has some different things here. You can see that it has ways you can label the graph. Here's the show regression curves. It actually has curves you can graph over the scatter plot, but we're just going to stick with the lines today. And then we're going to click OK. And there's our scatter plot. Looks very similar to the one we saw in StatKey. Also, you have the actual line. Here's the regression line formula. There's the y-intercept, negative 3.211, and the slope, 0.330. I can see the dots are actually pretty close to the line. So you can kind of see that. So that's under graph and scatter plot. But if we really want all of the statistics, this is not the way to do it. We want to go to the correlation and regression section. So you go to statistics and then click on correlation and regression and then linear. Okay, so if you're doing a basic correlation and regression study and you want all the numbers in one place, this is the way you do it. You go statistics, correlation and regression, linear. And we'll kind of see here, if I click X as my waist size and Y as my body mass index, and I click add series. Now there's a few graphs you can get. Notice it offers you a significance level because this goes with the correlation hypothesis test. Now we haven't really talked too much about the correlation hypothesis test, but this is where you'd get all the numbers for that. Here's it says show the scatter plot. Yeah, I always want to see the scatter plot. If you click the show legend button, it puts a title for you on the scatter plot. But right here it says show regression line. Yeah, I want to see the regression line also. Now here's some of those other graphs that I was talking about at our last lecture, the residual plots. So if you click residual plots, you'll see a bunch of different ones. The two that I was talking about in the last video was this one, the residuals versus X variable. That's called the residual plot. And the histogram of the residuals. So those are kind of the two main ones that I was discussing in our last video. So if you ever want to calculate those, you can have the computer calculate those for you. Let's see what it looks like. So here's our scatter plot, right? There's our scatter plot right there. Looks good. The dots are very close to the line. I'm seeing a positive linear relationship here, pretty strong. The dots are very close to the line. Here's my residual graphs. So here's the residual plot right here. And here is our histogram of the residuals. Okay, there's our histogram of the residuals. So those are those two graphs that I was showing you yet last time. Now let's look at the numbers they gave us. Notice there's a null and alternative hypothesis. This is actually the Greek letter rho. We'll get more into this when we do the correlation hypothesis test. Here's your R values right here, R, and it's right under test statistic. They actually offer a t-test statistic with the correlation and regression study. Usually that's the one we use for the hypothesis test, this t-test statistic right here. And here's the critical value. But here is the R value, 0.8799. And again, that is very strong positive linear relationship, right? We learned that last time. Notice this is interesting. It gave us a critical value for the R. Now this is very interesting. It's kind of telling you, remember how I said that usually it's got to get in the 0.2s or 0.3s to be considered some linear relationship. It's not no linear relationship at all. And the computer thinks that the R value's got to be at least 0.2199 to be considered at least some linear relationship. I kind of like to think of this as the beginning of your weak linear relationship zone. Here's our regression equation, y equals b0 plus b1x. Remember, b0 is the y-intercept, and b1 is the slope. So here's the slope right here. If you just put this number where it says b1 and put this number where it says b0, you actually have your formula for the regression line. Now here's a couple other nice things. Right here it says r squared. 0.7742, right? And so it's got my R squared. So I know that 77.42% of the variability in body mass index can be explained by the waist size. So again, that's our R squared, or coefficient of determination. Standard error of estimate. I'm not a big fan of that term, the way but that actually is the standard deviation of the residual errors. So this really right here is the standard deviation of the residual errors. Okay, so I sometimes like to retitle it. I'm not a big, some people call standard deviation of residual errors and they shorten it to say standard error, but that kind of creates a lot of confusion because we already learned that the standard error was the standard deviation of a sampling distribution. So again, this is, I prefer to say standard deviation of the residuals, or you'll hear some people say standard deviation for correlation or things like that, but I prefer that title. And it's 2.3714. Very difficult calculation. The computer did it, like say, in a split second. So this is telling me, remember, two meanings we said of standard deviation of the residuals when we looked at the residual video. The one is that it's the average distance from the line. So the points in the scatter plot are on average about 2.37 kilograms per meter squared vertically from the line. It'll always be the same units as the Y. So body mass index unit. It also tells me the prediction error. So if you try to predict somebody's body mass index based on their waist size, your prediction could be off on average by about 2.37 kilograms per meter squared. So the main thing to remember, this is your prediction error, how far off your predictions could be. Okay, let's look at another one here. So if we look at this one, we can go statistics, correlation and regression, linear. And now I'm going to do the weight of the cars and the gas mileage of the cars. Again, you got to click this Add Series button. I always forget that for some reason. Click the Add Series button. And again, we'll use the same scatter plot. We want the residual versus X variable and the histogram of the residuals. Again, we'll get more into using these residual plots when we get into the correlation hypothesis test, because these are part of the assumptions for the correlation hypothesis test. So we'll push OK. So there's my scatter plot. I can see the strong negative linear relationship. The line is going down from left to right and the dots are very close. I don't have any dots that look like they're really far off vertically from the line. Everything looks pretty close. I can see the, here's the histogram of the residuals, kind of looks roughly in the ballpark of normal. Also, this